work of the past decade or so, looking at evidence for synchronization in the global earthquake catalog. And the most recent paper on this topic just came out this year with my colleague Dave Menson at UNAVCO, but the kind of concepts behind this body of work really benefited tremendously from years of discussions with my colleague Mahat Evan at Harvard and Roger Billum at CU Boulder. So I'm going to maybe extend the usual introductory material a little bit for this work, because I'm pulling in some ideas and concepts and principles from other areas of physics and mathematics, and just to make sure that we're all kind of on the same page. Oh dear, that's gonna be hard. Hang on. I can't actually advance my slides at all.
Maybe try clicking it with your mouse.
I have.
You can click the arrows in the left corner.
There we go. So let's start with just the basic idea of what is synchronization in the first place. So hopefully you can see this short YouTube video. This is 64 metronomes, and synchronization is a really fundamental property of oscillatory natural systems that basically argues for the phase alignment of repeating objects over many cycles. And so this is a kind of classic demonstration of synchronization. What you can see are these 64 metronomes in a video, and they're all started with arbitrary phase and arbitrary initial displacement. And then over time, as you watch, you'll see that sets of them and eventually the entire array of oscillators become phase aligned. And this video has a couple of, kind of demonstrates a couple of critical underlying principles in synchronization that are going to be important throughout the rest of my talk. The first is that synchronization is a nonlinear interaction of oscillatory systems. So it's different from this kind of basic principle that we find throughout earthquake mechanics of direct triggering. That is a much simpler, more linear interaction. So adjacent metronomes aren't actually just like smacking each other so that over one cycle they instantly become phase aligned. Instead, what's happening are very small changes in dynamic stresses in the whole array or the whole domain where the oscillators are incrementally clock advance or clock retard, or phase advance or phase retard adjacent oscillators, so that over many cycles these small nudges to the phase eventually result in phase alignment of individual oscillators. And this is really important because the magnitude of the stress required for direct triggering is large. You know, it takes a certain amount of force to move one of these metronome arms in a specific way. But the amount of stress required to synchronize or to phase align these objects over many cycles is orders of magnitude smaller. And in fact, there are some famous experiments trying to look at what the stress magnitude threshold is for synchronization. And it's very hard to identify what the kind of minimal stress required is. In fact, there are some classic experiments with metronomes in a large room on isolated foundations, so they're completely mechanically separated from each other, and they still phase align over many cycles simply due to the stress of the sound wave from the ticking of the metronome. So incredibly tiny stresses over a large number of cycles can lead to this nonlinear interaction where you exponentially gather individual oscillators into phase alignment. The other thing that this video demonstrates, I think, nicely is that there are a lot of emergent complex patterns, and I'll go back to here, in synchronizing systems. So if you watch that for a while, you would see that groups of metronomes synchronize to each other, but occasionally you have excursions of individual metronomes out of phase alignment. You can also have complicated patterns like synchronization waves, where sets of oscillators have phases that are not perfectly locked to each other, but shifted by some increment of pi. And then you can also see oscillators that are antiphase aligned with the rest of the array. So there are some really rich and complicated interactions in even this very, very simple system where all of these metronomes are regular oscillators with the exact same period. And then, of course, synchronized systems can also have harmonics and overtones in them. So this is a really beautiful paper that I just stumbled across from 2018 that looks at oscillatory systems in the coupled Earth and solid Earth ocean atmosphere that are associated with El Nino cycles. And what you can see, or what the authors argue in this paper, is that there are certain time intervals when, because the period of these different oscillators are different, that they're phase misaligned, and other time intervals when they're phase aligned that lead to the kind of superposed harmonic cycle of regular El Nino and La Nina systems that we observe on the planet. But of course, some of the more interesting emergent behaviors of these systems of oscillators include synchronization waves and complicated beat patterns. So in this plot on, I guess, my left, I don't know what it is for you, your left or your right, what you can see is the results from an experiment using electronic oscillators, where initially the oscillators are at some arbitrary phase, but then over time they organize not into a completely synchronized system, but in a set of propagating waves of sets of coupled oscillators with phase locking. So you can see on the time axis and the space axis here, as you get to a large, at least in this case, in a circular electronic array, a large number of oscillators that you can have sets of them with phase arrangements in a variety of different patterns. And then this other plot here shows, in fact, the true richness of these kinds of systems. So this is a bifurcation diagram, or a phase diagram might be more familiar terminology to those of you who are geologists, for just a simple 2-element integrate and fire system of oscillators. And each of the colors in this phase diagram is a different interacting charge-discharge pattern. So you can think of this as 2 oscillators that are beating against each other with, for example, this blue domain is oscillator A triggering oscillator B, which triggers oscillator A, which triggers oscillator B, in a simple AB-AB pattern. But obviously this phase diagram is hugely complicated, which with each of these colored domains, a different firing pattern. And in fact, the black areas of this phase diagram represent chaotic firing of those oscillators. So even with just a 2-element system, you can get this emergent complexity for the interactions of those oscillators. And this phase diagram is a good segue because these are something called integrate and fire oscillators, which is the oscillator model that we have used for the earthquake cycle. So what is an integrate and fire oscillator? Well, the ones you might be most familiar with are neurons in your brain, or heart cells, or a few different kinds of electronic elements. basically the model, the simplest model of integrate and fire oscillators is a quadratic integrate fire model, where you can see the charging pattern here on my left, where you have some kind of object that has to be charged after a discharge, and then once it reaches some threshold, it can fire again. So for example, in a neuron, you have inputs that come from pulses of ion pulses from neighboring neurons as these little input pulses. And those pulses excite a neuron, an adjacent neuron, where charge in the neuron or a potential across the cell membrane builds until it reaches some threshold value, at which point that neuron can discharge, produce a peak voltage, and stimulate its neighbors. But the basic principle here is that there's some kind of input of energy into the system until some threshold is reached, and then after that threshold is reached, that system can discharge the entirety of the energy stored in the system, as it was being charged with incremental pulses. And we actually think this is an entirely reasonable analog for what we typically call the earthquake cycle. So in the earthquake cycle, obviously, if you look at earthquake systems or earthquake mechanics from an energy or a work budget perspective, what you have are kind of incremental inputs of energy into the system that are stored as elastic potential energy over a long interval. And obviously, in the kind of textbook example, this is a steady charging by tectonic energy, storing elastic potential in the crust. But of course, what you're really storing is not only the input tectonic elastic energy, but also all of the static stresses that are applied to some arbitrary fault patch, including those that come from surface mass loading or tides or neighboring earthquakes as well, that provide a static stress change to the fault patch domain. And we know that earthquakes have either these time predictable or slip predictable characteristics, and these are characteristic features of integrate and fire oscillators in general, not just earthquakes alone. That is, that you can estimate the total work or the total moment in the earthquake case available by knowing what the input of potential energy was to the system going forward. And this is a more nonlinear integrate and fire oscillator than that quadratic model, in the sense that once the threshold potential is reached for an earthquake, it may or may not happen instantaneously at that point, right? If it reach some threshold potential, then we would have this nice characteristic periodic behavior, and we would never have to worry about earthquake forecasting because we could just count the time since the last one. But more complicated kinds of integrate and fire oscillators are typically time predictable or slip predictable or discharge predictable if you're talking about electronics. So that's kind of the overarching background. And I would say now we move into the more conjectural part of this talk by saying, suppose that we understand earthquake mechanics to be at least analogous to a generic integrate and fire oscillator. And we also observe almost universally in physical and electrical systems that integrate and fire oscillators do have synchronization. They have complicated synchronization. It's much messier than the metronome problem, but they do have extremely well documented, both theoretically and observationally, very well documented synchronization behavior. So if we say, well, maybe earthquakes are kind of like integrate and fire oscillators, and integrate and fire oscillators almost always have emergent synchronization, then it's reasonable to ask the next question, which is, do earthquakes have synchronization properties? And then the tricky piece, next step is, how could we test this? If our hypothesis is indeed that earthquakes are globally synchronized, how might we test that hypothesis? And the simplest way to test, of course, as with most things to do with earthquakes, is to do a bunch of numerical simulations. And these tests have been done either explicitly or implicitly. So in the explicit case, there's this really nice Samuelson-Smith paper from 2013, where they simply created sets of earthquakes that are dislocations in an elastic half space that have a perfectly periodic behavior. So they have a regular recurrence interval. And if you start that set of earthquakes at arbitrary phase over time, I guess theoretically, unsurprisingly, but interestingly, they do phase align. So this upper panel here shows the output of simulations where each of these circles is an individual earthquake, and all of these earthquakes are started at some initial condition with the arbitrary phase, and then over multiple cycles, they do just what the metronomes in the movie did, which is they incrementally nudge adjacent clock timing or adjacent phases so that over many cycles they become completely phase aligned. And then since in this simulation, these are perfectly periodic earthquakes with a constant recurrence interval, once a set of earthquakes becomes phase aligned, that means all the earthquakes happen at once, they stay phase aligned forever because you just have the same, you're just counting the same interval until the next set of events. Or in a slightly more complicated simulation where there are sets of model earthquakes with two different recurrence intervals, so these open circles and these closed circles, what you see as the sets of events with the same recurrence interval, so the same characteristic fundamental period, become phase locked to each other and beat against each other, since they have different recurrence intervals. So all of these open circles become phase aligned over many cycles, and all of the closed circles become phase aligned over many cycles, even though they start with some arbitrary phase relationship. So as I said, this is sort of unsurprising because this is what we expect to be a fundamental nonlinear interaction between regular oscillators. But there's some interesting pieces also revealed in this Richard Singer and Dietrich article from 2012 that presents the RSQ SIM catalog. So for those of you who don't know, which is probably exactly none of you, the RSQ SIM catalog is a 20,000 year simulated earthquake catalog for California using the California community fault model embedded in a homogeneous elastic space. And this particular simulation does not have any explicitly included oscillatory characteristics. So all it includes is rate and state friction and the interactions of faults through the basic continuum mechanics principles of stress in a homogeneous space with faults as dislocations in that space. And so what you can see in the RSQ SIM catalog is that in general, for these smaller magnitude events, they follow this red line. So this upper panels, these are the natural catalog of California earthquakes. This is the 20,000 year simulated catalog. They follow this red line, which is the power law distribution, so Gutenberg, Richter, until you get to these longer inter-event time interval events. And those appear to generally follow this blue line, which is the Poisson distribution, which you can think of as a random walk in time distribution. But if you look closely at these larger magnitude events, and especially in the largest magnitude events, what you see is that the RSQ Sim catalog doesn't actually have a perfectly Poisson distribution of large rare events. In fact, there's about a factor of 5 difference in the probability of events with certain inter-event times or inter-event intervals compared to those with the least likely inter-event intervals. So the SCIC crowd calls these super cycles. These appear to be emergent from the basic mechanics of the RSQ Sim catalog, showing that there is some phase alignment in the sense that there are preferred or there are certain inter-event intervals that are much more common in the catalog than other inter-event intervals. So this is characteristic of integrate and fire oscillators that are partially phase aligning with each other. It means that there are common inter-event intervals that are closely related to and proportional to the characteristic timing period for charging of those fault patches. So great, in simulations, we at least have like tantalizing hints that earthquakes are behaving like integrate and fire oscillators that have some emergent temporal structure, particularly for the largest events. But again, this is simulation, and what we would really like to do is look in the natural earthquake catalog and see if we can see any evidence for real earthquakes where we don't completely understand every component of their physics yet, but still have some evidence for integrate and fire type synchronization. And so what we would like to do is do some statistical analyses of the natural global earthquake catalog. And what we would expect is for our hypothesis that earthquakes do have synchronization, we should expect to see either or both of these two key characteristics. One is temporal sets of events with the same natural period, and the other is variability in the probability of inter-event intervals that deviates from the perfect Poisson distribution. So we could see either or both of these patterns and use that as suggestive of integrate and fire style synchronization in the natural catalog. But we have a problem because the natural catalog just frankly kind of sucks. It's really short, right? And it doesn't have as many events as you would like in it because it's short. So it's short and it's incomplete, unlike RSQ Sim, which is 20,000 years of every single earthquake in the simulation being accurately captured. So this is a plot of the PagerCat catalog, which is an older catalog, and then magnitude slices out of the global earthquake model, which has become the sort of gold standard for the global earthquake catalog. And you can see lots of things in this plot. So this is 18,660 events in the GEM catalog. One is you can see at these smaller magnitudes, so up here in the plot, that they are obeying that power law Gutenberg-Richter relationship in the sense that these lines of different number of different magnitude events are approximately parallel to each other, if this y scale is on a log scale. But you can actually see the transfer to the Poisson distribution, because at these higher magnitudes down here, there's a lot more variability in the temporal structure of the number of events in a given year. And you can also see a problem of completeness that's biased by event magnitude. So it looks like, at least within the high level of variability, that the global earthquake catalog is close to complete, maybe back as far as 1910 or just before. But if you look at these lower magnitudes, so for magnitude 7, which is the red line for GEM, maybe complete starting in the 20s, early 1920s. And for magnitude 6, it's pretty clear that the even our best catalog, the GEM catalog plus the supplements, is incomplete before 1930, or maybe even all the way, doesn't get complete until all the way after World War II. So we're looking for temporal patterns in earthquakes that would be more pronounced at higher magnitudes potentially, but we have very few higher magnitude events, and we have a very short catalog in time. So we have this horrible challenge of trying to resolve these pretty subtle signals using a random snapshot subset of a much richer catalog that maybe would be would give us the statistical resolving power if it were much longer, or if it were much more complete. So we have two choices at this point. We can say, okay, well, cool idea. Let's wait 10,000 years until we have a complete catalog. That's not very satisfying, because I'm definitely not going to live that long and I want to test my hypothesis. Or we can select different statistical methods for different subsamples of the catalog, or different kind of components of the catalog, and try to balance our ability to resolve temporal structure against sensitivity to completeness and duration issues. And so I guess obviously we're going to try strategy 2 first, and if that doesn't work, then we'll wait 10,000 years. But in order to do that, we have to do one transformation of the data. We have the absolute temporal information from the natural catalog, but we don't know for each of the events that this catalog represents, what is their characteristic period. So what we would expect to see, as I said in the test, is that events gather together in time. So they have temporal structure based on their natural period. And so we need two pieces of information about earthquakes in order to test for that pattern. One is their absolute timing, and the other is their natural period. And so the best we can do is actually estimate a renewal interval for each event in the earthquake catalog. So, you might initially have said, well, let's use the recurrence interval. That must have something to do with the natural period of these integrate and fire earthquakes. But it turns out that maybe 1% of the earthquakes in the GEM catalog have a robust recurrence interval estimate, probably even less than that. And most of you listening will also know that recurrence interval has huge variability. So we really, even if we picked average recurrence interval, it would mean we just didn't have anything like enough events to work with, and the variability of that measure is actually perhaps not unrelated to the interaction of earthquakes one with the other. So we need something that better approximates and more systematically and consistently for the whole catalog approximates what the natural period of each of these events is. And so we use something called the renewal interval as a proxy for that. And the renewal interval argument comes from that moment or energy model of earthquake mechanics, which is simply that it represents the amount of time required to store the elastic potential that is released during an event of that magnitude, such that the renewal interval just equals the average slip in the event, which we get from the magnitude of the event using the Leonard 2010 scaling that's built on an assumption of conservation of energy. So we take magnitude, figure out the average slip, and then divide by the charging rate, which is the coupling for the fault system on which that earthquake occurred times the tectonic velocity across that boundary. And so this gives us probably something like a lower bound on the renewal interval for the system. And we use consistent coupling coefficients from the Berryman compilation and tectonic velocities just from the global plate motion, no net rotation solution. And then for places, for earthquakes that are not on a known boundary or not on a boundary that has an coupling estimate or a tectonic velocity estimate, we use the regional literature to estimate or to find a fault slip rate for that location. And when there's no coupling information, we assume a coupling coefficient of 1. So again, this is giving us a bound on the amount of time it takes to store the potential energy that's released with slip as slip during an earthquake. So at least we have a consistent estimate of natural period for every event in the catalog based on this reasoning. But then of course we are still stuck with the basic bias of having a catalog that's just a really brief 100-year or so snapshot of events, and that is we are strongly biased towards events that have very short renewal interval. And in some ways that's fairly comforting because you would expect events that with very short renewal intervals happen all the time. So if you're going to take a little snippet out of a much longer history of seismicity, you should expect to be oversampling these short renewal interval events. And indeed we are. You can see that the modal renewal interval in the catalog is about 20 years. But there are some interesting patterns in the catalog, specifically, different major subduction boundaries have different modal renewal intervals that we might be able to leverage in derived analyses. And so then back to my argument that we should try to use different statistical tests to maximize our ability to look for this temporal structure relative to the renewal interval of the system. We're going to use 3 different approaches. One is Schuster spectra, and this approach can nominally resolve temporal patterns as long as the catalog, but we actually see empirically that we can't resolve temporal structure much longer than about a quarter of the length of the catalog, so it can resolve patterns in timing of earthquakes with periods of sort of 25 years or less. And mainly that's because the resolution of the Schuster spectra decreases as you lose completeness. So as the catalog becomes less and less complete, the less the Schuster spectra can definitively resolve characteristic frequencies in the temporal structure of events. But within that window of 25 years, you'll see it has very high resolution for short period effects. And then Fourier spectra can sort of nominally resolve half or maybe 3/4 of the length of the catalog, so kind of 50-year period variability in earthquake productivity. The Fourier spectra are more tolerant than the Schuster spectra of incompleteness. And systematic completeness changes just produce DC power in the power spectrum. So if we're getting more and more events over time because we have greater completeness, you can see that as a DC shift in the spectrum. And then finally, topological approaches can resolve organization in time of earthquakes at intervals much longer than the length of the catalog, because they're sensitive to clustering of events in time. And those methods are highly tolerant. In fact, they're designed to tolerate highly incomplete and very noisy data. So they have considerably less kind of resolving power than the Schuster approach or the Fourier approach, but they're much more tolerant of incompleteness and noise in the catalog. So just to show you a little bit more about these methods. So the Schuster spectra calculate the inter-event interval, so the time between events of every single pair of events in the whole catalog, and then they compare the distribution of those inter-event times against a Monte Carlo suite of random walk synthetic catalogs. So on the left here, you can see the Schuster spectrum for a random synthetic catalog compared to lots and lots of other random synthetic catalogs, random walk synthetic catalog, and you can see there's nothing even approaching statistical significance in this. This is the Schuster spectrum for a random catalog, except that 10% of the events are systematically separated by 1 year from each other. And you can see that the Schuster spectra has no problem resolving even a 10% bias in the temporal distribution of events. So it's very good at finding these patterns, at least within the resolution window for the spectrum. Everyone listening to this talk will be comfortable with Fourier spectra, which simply deconvolve a time series into the sum of perfectly periodic contributions and then map the amplitude of each of those contributions. And then finally, some of you may not know so much about topological data analyses. These actually work by taking some arbitrary set of objects with any number of characteristic parameters to them, normalizing the variance on all of those parameters, and then applying some kind of statistical metric to those parameters. And there are a variety, they're large. You can basically apply whatever statistical metric you want, from the mean to the variance to much more complicated Gaussian mappings, for example, on the distribution of parameter values. And then using those statistical measures of the characteristics of the event parameters, calculating a distance metric that is a proxy for the similarity of individual records. And then using that distance record to create a topology or a network that represents the data in terms of how similar or different individual records are from each other. And so how are they arranged in space according to their basic characteristics. So basically the topology that comes out of this analysis is such that events or records that are very similar to each other are very close to each other in the topology and are connected with a direct connection, and events that are very different from each other are far away from each other in the topology, and events that are close to each other but not connected have some similarities in some parameters, but critical parameters are different from each other. So the shape of the network represents the variability of the characteristics of the objects in the data set. So let's get to the results. Here are the results for the Schuster spectra. And what we did is divide the catalog, the whole natural catalog, into bins based on the renewal interval of the events. So remember, what we're looking for is a consistent structure such that earthquakes with more similar renewal intervals behave in a similar way to each other, and events that have very different renewal intervals are behaving very differently from each other in time. And so what you can see in the short renewal interval bin is that the Schuster approach can resolve a bunch of very significant characteristic inter-event intervals. So there's an annual term, there's this 2.5 years, and then there's this very consistent kind of 20-year peak in Schuster probability that tells us something about a very common inter-event interval in this subset of the catalog. If you look at the next longer bin of renewal intervals, you'll see you have much less power or much less bias toward shorter inter-event intervals, but we still see these peaks at longer periods. And then if you look at the longer renewal interval events, there are no statistically significant recurring or biased inter-event intervals. And so you can see a kind of temporal organization that is at least proportional to the characteristic period of these events as expressed by their renewal interval. So this is more or less what we would expect. If we look at the Fourier analysis, you see something like the same pattern again, which is these short renewal interval events have a ton of power at the modal renewal interval, which is about 26 years. So we see for short renewal events, both the 0 to 25 renewal events and the 25 to 50 renewal events, there is a pretty regular 26-year cycle in earthquake productivity globally. But then looking at these longer renewal interval events, we see basically no important peaks in the power spectrum. And so we're stuck then with using the topological data analysis to look for now not a repeating period, because any repeating period that we would expect from synchronization arguments would be much longer than the length of the catalog itself. So there's no way that we could see it. But what we would expect instead is to see very strong temporal clustering of earthquakes with a similar renewal interval. So what that means in slightly different words is like, for events with very long renewal intervals, longer than the duration of the natural catalog, we should expect those to be really rare in the catalog and occur, basically once every 400 or 500 years, because that's the renewal interval. But instead, we see sets of events with those long renewal intervals happening very close together to each other in time. And let me orient you to these TDA plots, because man, it took me years of staring at them before they made any sense to me. And that seems to be a common occurrence. So this is the same topological network. It's just colored differently for both of these plots. On this side, the coloring is the absolute timing. So blue is the early 1900s, red is after 2000. And so you see you have earthquakes at all times. And this in this network, the coloring is by renewal interval, where the bluer events are those short renewal interval events. And you can see they're happening at all times throughout the catalog at a pretty steady rate. But these very long renewal interval events are happening in these very tight temporal clusters. So these 4 groups that I've identified here and labeled, they happen very close to each other in time. And in fact, you can see this, that the topological analysis is showing this pattern even down to the shorter renewal interval events in an interesting way. So again, on this side, these are all colored by time. And on this side, they're colored by renewal interval within the bin. And so these very short renewal intervals are basically happening all the time in the catalog. They have these inter-event intervals and this periodicity that the Fourier and the Schuster spectra revealed, but they're not tightly clustered in time because you have superposed sets of events happening at all times. But as you go to the longer renewal interval bins, what you see is, again, this is time, so the time sequence, and this is renewal interval, where this part of the topology are the longer renewal interval events. And you can see this really consistent pattern that the longer the renewal interval, the patchier the events are distributed in time. So the more wholly the network comes. And then as you get to this 50 to 100 year renewal interval bin, you start to see these very isolated clusters of events with these long renewal intervals that are telling you that these rare events that take a long time to reach their discharge threshold don't happen at random in absolute time. They tend to cluster together very strongly. And so all of these patterns are really consistent with our expectations from our hypothesis. So just getting to some implications, there's certainly statistical evidence for synchronization in the global earthquake catalog at a range of periods. We can use that regularized or that biased event interval information or the temporal patterning to do interesting things with forecasting. For example, faster subduction boundaries have more regular inter-event intervals at short periods than slower ones. And the Himalaya, one of the slowest of all, has no regular inter-event interval within the 25-year resolution of the Schuster test. So we could look for variability in earthquake productivity as a function of the rate of loading of a major tectonic boundary. We can see regular periodicity, so peaks in earthquake productivity in the whole global catalog at some specific intervals. In particular, this kind of 25, 26 year period shows up over a wide range of magnitudes. So we could use that to say, okay, we're entering an interval where we expect higher than average earthquake productivity globally or lower than average earthquake productivity globally. And then I think the most important kind of forecasting tool is that you have these global teleconnections for the largest and rarest earthquakes, these events that have a very long renewal interval, sort of hundreds of years. And if you see a couple of events with long renewal interval, you should expect to a very high degree of statistical significance that there will be other events of similar renewal interval happening close to those first events in time. Okay, so these are all the statistics, and I know I'm running out of time, even though I promised we'd have lots of question time, so I won't go into that, but there's a very high degree of statistical confidence that these large, rare, long renewal events are clustered in time. And then this also implies a mechanism for other things that people have recently reported in the literature, which is like seasonal loading, in training, earthquake productivity, for example, where you have, what should be just way too small stress changes like those from solid earth tides or the weight of snowpack actually producing changes in earthquake productivity. Well, synchronization and its cousin entrainment mean that as long as those are periodic forcings, they can be really tiny and still phase align earthquake cycles. And then the last implication is, of course, it's a small world. So our globe is sufficiently small enough and sufficiently highly mechanically coupled that earthquakes do appear to talk to each other over the whole planet over many earthquake cycles. So I'll leave it at that, and you guys can all tell me how very wrong I am.
Thanks, Becks. We can take questions if you're able to stay a little longer.
Or you can just sit in stunned silence and we'll call it good.
I think the easiest way, again, is still just to do the raise hand function, or if you just want to drop it in the
Ellie,
chat.
your lips are moving, but you might be muted. Or actually, no,
well, in the humanities, what is the reason that anyone would think that calculus is the language God talks? Why should a
Now I'm hearing something about calculus.
Why should a normal person?
Bex, I think you're playing something.
By the way, I don't feel necessarily you need to learn calculus. This is a story about a
This is strange.
The language God talks.
I do like calculus.
I want to try to illustrate what I think he might have meant.
I think you started playing a YouTube video again.
Electricity and magnetism.
Okay.
So electricity, here's a picture of my daughter, Leah, my older daughter. I have two daughters. So when Leah was 4 years old, there she is at her grandmother's house, and she's playing on the bed, and it was winter, and static electricity.
I'm glad it wasn't like a deeply embarrassing YouTube.
I think we have a question from KGA. I'm not sure who that is.
That's Duncan using his wife's computer.
Hi, Duncan.
So I would just like to have an explanation of where the lines come from in the figure with all the red dots, with sloping lines that depend on magnitude and renewal interval. That's the point at which I began to feel slightly unmoored.
Okay, so lines come from, those are basically lines of events of different magnitude in places that have a constant loading rate, basically. So I can, now that I've got...
Okay, so as the magnitude goes up for constant loading rate, the renewal interval just goes down. Or, yeah.
Correct.
Yeah,
Yep.
Okay, all right.
It's that simple. But of course, each of those streaks is like a different plate boundary because each boundary has a different product of coupling and loading rate.
Right, okay, anyway.
Or they might be, they might be sort of coincidentally two boundaries that whose product of those two numbers is the same thing, but yeah.
Tianzin, go for it.
Oh yeah, so I have a question about how you define reoccurring events. Do you define them as earthquakes happening on the same fault or at different times? Is that the way you define it?
So we never define a repeater event because we simply just don't have a long enough catalog to capture really hardly any of those. I mean, there are a handful of known repeats at this point in seismology, but what we simply do is, that's why we use that renewal interval for each event in the natural catalog. We just calculate the amount of time that it took to accumulate the elastic potential energy to produce that event. And we assign that as the natural period for that event. So we don't have to in order to like pursue this statistical line of reasoning, we don't have to find actual repeaters.
Oh, I see. So the period of each event is calculated by computing that renewal interval.
Exactly. So we assign that renewal interval as the like natural characteristic period for that event.
I see, and you use that to come up with the statistic, the like the Schuster spectrum and the Fourier spectrum.
Yes,
Okay,
exactly.
I see. Thanks.
Yeah. I wish we had like the natural equivalent of the simulated California catalog for the entire globe, because then we could do it the way you're suggesting, which is actually look at the true period, characteristic period for each of these events, but it's not possible.
Thanks.
Yeah.
Kong, do you have a question? Kang? Sorry.
Yes, I think Chris Shields had a paper about 10 years ago in which he also noticed that for certain regions, the larger earthquakes tend to cluster in time, tend to synchronize in time compared to the repeat interval. But he also noted that for those earthquakes, for those regions, the sleep rate on those faults tend to have a relatively small sleep rate, usually on the order smaller than 1 millimeter per year. And also he noted that for this type of event clusters, the faults are usually evenly distributed and typically on a regional scale, say on the order of a few hundred kilometers. In your analysis, do you see any characteristic spatial extent across which the events are clustered or synchronized?
So you would expect from theoretical arguments for the kind of characteristic cluster length scale to scale with the periods of the event. So like you do see, there are a bunch of papers, including the one you mentioned, but there are lots of others that show that for small patches with many, many faults, the microseismicity has some temporal structure. And that is easier to capture statistically because microseismicity is, one, has very short renewal intervals, right? You don't need to store a lot of potential energy to have a magnitude 1 earthquake. So you can get many cycles in that case, but you probably have interactions over a relatively short length scale. So you see these kind of like more localized domains of synchronized microseismicity. And then at least the theoretical argument would be like, as you increase the renewal interval and the total potential energy of these integrate and fire oscillators, their reach is longer. But again, there is no bottom threshold for this that anyone can figure. Like if you have enough repeat cycles, even very, very tiny changes to the static stress can, over many cycles, align phases.
Thanks.
Mm-hmm.
Any other questions for Becks? Duncan, go for it.
I'll come back again. So if I were to look at a map of long renewal events, would I be seeing mostly intraplate events plus a few really large events on plate boundaries? I mean, those two things seem like they would be what would get you a long renewal interval. It either has to be really big or the local strain rate has to be really small, which means intraplate.
That's exactly what you do see. And if you look at those like sets of, we did actually like use the topological data analysis to identify some groups of earthquakes with similar renewal interval that happen very close together in time. And if you look at those maps, and they're actually, I think in the supplement of the Bendick and Billum paper, you'll see it's exactly that. It's big events on plate boundaries and then some smaller intraplate events or events on poorly coupled or very slowly loading boundaries. But it's interesting because I think, the instinct would be to fall into the trap of direct triggering and think that maybe events on fast subduction zones should always happen together and events in slow places should happen together, but it doesn't seem to matter the tectonic setting. It's really grouping common renewal intervals. And that's the small world argument, right? If this is true, which I will say if for sure, then you're teleconnecting systems with similar timing characteristics, but not necessarily similar tectonic characteristics.
Any last questions for Becks? All right, I guess with that, we'll say thank you and hope to see everyone next week. Awesome. Thanks, Becks.
Thank you for having me.